Okay, so now let's continue on with our study of extensive form games, and in particular, now let's look at a different form of reasoning and by which we can make predictions in the game, and in particular, let's look at solving games backwards. So what does that mean? Let's look back at the Centipede game and begin to use some reasoning by looking at the simplest possible decisions first and then moving back to the more difficult ones. So the idea is we'll start by looking at the last part of the game. So we'll look at decisions just preceding terminal nodes. So here, for instance, player 2, if they're called upon to move, they've got a choice of either passing or stopping. So we look at the 64 and the 128. The conclusion is if player 2 was ever put in this situation, they should stop. So a rational player that's maximizing their payoffs, there's only a single action which they could choose in that situation, which is to stop. Therefore, if we're consistent with maximizing behavior, the prediction is that then player 2 should stop at this point. Now here's then when we begin to solve the game backwards. So anticipating that player 2 is going to stop at the last move, then player 1 is faced with either 32 or 64 if they're called upon to move at the second to last node. So what are they going to do? Well, now there's a clear prediction for them, which is to stop here. So we end up with stop at this point, stop at this point. If we keep moving back, we'll end up with the same logic. Now player 2 is looking at 16 or 32. They should certainly stop, and so forth. So it unravels all the way back to the beginning. What's different between this and Nash equilibrium, what we're getting here in terms of prescription, we still have the same prediction that we should stop at the first node, but we're also getting a prediction that the only thing that's possible at every other node is to stop. So here we're using logic which says if the player's put in this situation and they understand that other players are rational and maximizing expected utility. So here we have player 2 stopping, therefore player 1 understanding that player 2 has an incentive to stop, chooses to stop. Player 2 understanding that player 1 understands that player 2, and so forth. So we're using iterative reasoning, we're reasoning backwards through the game, and that gives us a unique prediction of stopping at every single node in this game. So now we have a unique backward induction solution. Which is stop at every point, so every node. So we end up with something which is different from the Nash equilibrium. In this case, the outcomes are exactly the same in terms of stopping at the first node, so the payoff predictions are the same, but the actual strategies are one of many Nash equilibriums. So this is a Nash equilibrium, but it's one of many Nash equilibria. So now let's take a look at a slightly different game. And this is a game where we'll end up with different predictions between Nash and backwards induction in terms of the backward induction is going to pick one of several Nash equilibria, and the Nash equilibria will allow us for different outcomes in the game, not just different strategies in the game. So let's take, this is an example of a game of perfect information. So typo there. Perfect information. It's an entry game. It's a classic entry game. So this is one where there's a monopolist who exists in a market. So they're enjoying monopoly profits. They're the only producer in a market. And there's another firm that's thinking about entering. And so the second firm has to decide if I enter, what is the monopolist going to do? So how will they react if I enter into this market? What are my expected profits going to be? So what are the important numbers here? We have some profit for the monopolist if they are the sole producer in the market. So M is their production or their profit number. The new firm has to pay a cost of entering. So there's a cost C. We'll take that to be not a positive number. So there's some cost to getting going in this market, opening plants and so forth. So there's some upfront costs that they have to pay in order to enter into this market. And then there's a question of what happens afterwards. And to keep things simple, we'll anticipate that the monopolist, so if the new firm enters, the existing firm can do one of two things. Either it can accommodate the new firm and share the market between the two of them, or it can initiate a price war and fight the new firm in some sense. And so just to keep things simple, we'll assume that if they decide to have a price war and fight the firm, then the profits are going to be zero each. So they're going to mark down all their products. They'll sell them at zero profits. But if there's no price war, then there's going to be some positive profits, pi. And in particular, we'll assume that pi is bigger than the cost of entry. So if they don't have a price war, then it's profitable for this new firm to enter into the market because they'll earn profits which are bigger than the costs. And to keep things interesting, let's assume that the monopolist profits are bigger than this pi, so that the monopolist would rather be alone in the market than have the new firm enter and accommodate it. Okay, so let's look at a simple version of this in the extensive form. So think of firm one as the new firm. They make a decision. They either decide to stay out of the market. If they stay out of the market, they get nothing, and the monopolist earns the monopoly profits. If firm one decides to enter, then firm two has a choice. They either fight a price war. If they fight the price war, they both get profits of zero. So zero for the firm that was already in the market, and the zero but minus the entry cost for the firm that entered. So here, the entering firm is going to earn a negative profit. They're going to lose money. Instead, they might choose to accommodate and just split the market. If they split the market, they get pi each. And the new firm ends up having to pay the entry cost. So they're both earning positive profits, but in this case, the monopolist is getting lower profits than they would if the other firm stayed out. Okay, so let's begin to analyze this. First, let's look at Nash equilibrium. Nash equilibrium of the game. So again, we just want to specify strategies that are best responses to the other player's strategies. So each player is making a choice. It's the best reply to the other player's strategy. So what does that look like in this game? Here's one Nash equilibrium. The first firm, the new firm, decides to stay out. The second firm would fight if the first firm entered, so they choose strategies of first firm stays out, second firm fights if the first firm enters, and then what do we end up with? We end up with the profits here of the monopolist profits for the existing firm and nothing for the possible entrant. Okay. Well, is this a sensible prediction in this market? It depends on what our beliefs are. Do we really believe that the second firm would fight if the first firm entered? Right. So this is a Nash equilibrium. In a sense, Nash equilibria are not always credible. And what does that mean, credible? So in this case, we have a strategy. The intended strategy of the second firm is to fight if the first firm enters, and that scares the first firm away. So by saying, look, I'll fight you if you enter my market, we won't earn any profits, is that a credible threat? So it's credible in the sense that if they're choosing this strategy of fight, if the first firm stays out, well, they're never tested. So if we all believe that that's going to be their strategy, then the firm one is actually staying out, and that's the best thing they can do. But if firm one entered, would firm two really fight? Backward induction is going to suggest not.